Let's define AND method, which is responsible for adding a new element to the heap while maintaining the heap property. We increment the real size attribute by 1, so the real size attribute will keep track of the number of elements which currently stored in the heap. So just by incrementing the real size, we acknowledge that a new element is being added to the heap, and the self-real size increment by 1 is essential for us to keeping track of the current number of the elements in the heap, which helps us to manage the capacity of the heap and ensure that the heap property is maintained after we add in new elements. And then we check if the number of elements in the heap exceeds the preset maximum size of the heap. If the self-stored real size is greater than self-stored heap size, it means that the heap is at its capacity and cannot accept any more elements. If the heap is at its capacity, we print a message adding too many elements to inform the user that an attempt to insert an element beyond the heap's capacity has been made. And next, we have to increment the self-stored real size by 1. So this is necessary because the self-stored real size was incremented earlier in the add method, right? So since the element cannot be added to the heap due to the capacity constraints, we need to undo the increment to maintain the correct count of the elements in the heap. Finally, the return statement is used to exit the add method without adding the element to the heap, as it cannot accommodate any more elements, and the portion responsible ensure that this heap does not exceed its maximum allowed size, which is self-stored heap size, by preventing the addition of elements beyond its capacity. If there's still room for new elements, we add a new element to the next available position in the array, which represents in the heap. If self-stored real size is less than or equal to self-stored heap size, we add a new element to the array, which represents in the heap. So the self-stored real size is the current number of the elements in the heap, and the heap at the self-stored real size refers to the position in the array where the new element should be inserted. So since the heap is a complete binary tree, so the new element must be inserted at the leftmost available position in the lowest level of the tree. So in this array representation, this corresponds to the position indexed by the self-stored real size. Let's assign the value of new element to the position in the array, which is specified by the heap at the self-stored real size. And then we assign the value of the self-stored real size to a new variable index. So the purpose is to keep track of the index of the newly added element to the heap, and the self-stored real size is the current number of the elements in the heap. Since the new element was just added to the heap at this position, which is indexed by the self-stored real size, it makes sense to set the index equal to self-stored real size for our further processing. So just initialize the index with the value of self-stored real size. We can easily reference the newly added element as it performs the necessary comparison and adjustments. And then we calculate the index of the parent node of the newly added element and assign it to a new variable parent. So in a heap represented as a complete binary tree, which is stored in an array with a root node at index 1, the relationship between a node and its parent and its child can be determined by using the formulas, which is the parent node index is index floor divided by 2, so the index variable contains the index of the newly added element in the heap. So just by using the formula index floor divided by 2, we can calculate the index of the parent node of the newly added element and store it as the parent variable. By calculating the index of the parent node, we can store it as the parent node variable, so we can easily reference the parent node as it performs the necessary comparison and adjustments. Now, let's try to perform shift-up operation, which helps us to maintain the maximum heap property after we adding a new element. So the shift-up operation consists a comparison of a newly added element with its parent node, and if necessary, we have to swap in the values. So this process is repeated until the maximum heap property is no longer valid, or a newly added element becomes our root node. So this while loop condition checks if the newly added element is larger than its parent node. If the index of the newly added element is greater than 1, that which means it is not the root node. If this condition is true, we just swap the values of the newly added element and its parent node, so the index of the newly added element is updated to the index of the parent node with the index assigned by parent. This is because the newly added element has been moved up to the tree to the parent node's position. So the index of the new parent node is calculated by using the parent is index floor divided by 2. This is necessary for next iteration of the loop. Well, the newly added element may need to be compared with its new parent node and possibly swap them again. So the shift up operation will ensure that the maximum heap property is maintained and after we inserting a new element into this maximum heap, right? So this loop will continue until the newly added element is no longer larger than its parent node or it becomes the root node.